Just wanted to welcome everybody to the cryogenics analysis panel. I think I am. I just want to introduce our speakers really quick. And as I introduce you, if you guys could turn on if you're able to turn on your cameras, please do. I know I didn't tell you guys cameras on, so if you're not camera ready, that's all right. So today we're just going to have a hour-long panel, just question and answer format with 6 of our cryogenic analysts across NASA and some contractors at NASA. These are some folks that have been doing cryoanalysis for several years and are really renowned in their field. I think this is going to be a very good discussion, so I'm looking forward to it. So thanks for joining us today. First, we're going to have Cindy Fortenberry. Cindy's the thermal team lead for NASA's LSP Launch Service Program, or LSP, and she's doing cryogenics modeling with liquid oxygen right now, liquid nitrogen, and liquid hydrogen for different launch vehicles. And she's also done independent verification and validation analysis of superfluid helium spacecraft. All right, next we have Daniel Hauser. So Dan's been performing both multi-node and CFD analysis of cryogenic systems at NASA Glenn since 2007. And he's been leading the CFM modeling efforts since 2017 related to the long-term storage and transfer of cryogenic propellants. So Dan, do you want to say hello?
Hey, Monica.
Hi, Dan. Next we have Olga Kartuzova. Sorry, Olga. She's been doing CFM modeling at NASA Glenn since 2009. So she's been conducting model development and validation using the ANSYS Fluent CFD code. And she developed and validated submodels, which then extend ANSYS Fluent capabilities in the areas of multi-phase heat and mass transfer and spray modeling. And she's also been providing modeling support in SpaceX for some collaborations with them. So welcome, Olga. Do you want to say hi?
Hi, thank you, Monica, for introducing me.
No problem. So next we have Alok. Alok's currently working on the CFM modeling portfolio project, and his primary responsibility there is to develop a GFSSP model of chill down and filling of cryogenic tanks and transfer lines. He's also working on flow boiling and tank pressurization with the GFSSP team. He's the co-PI of a 2-phase pressure drop correlation development for cryogenic transfer line chill down with the University of Florida. And he's been the primary developer of GFSSP for the last 25 years. And I believe they had a course earlier this week that is always worth checking out. He always puts a good course on. So, Alok, do you want to say hello?
Thank you, Monica. Am I audible properly?
Yes, sir, you are.
Okay, thank you.
Mm-hmm. And then we have Matt Moran, who you heard from earlier today in a short course. Matt's CFM modeling background has involved technology development, ground systems, and flight systems applications. Early in his career, he developed custom analysis tools with Fortran and C, then later with Excel and Visual Basic, and more recently with Python. His current work is focused on systems-level, first-order CFM analysis and trades related to human landing system projects and private sector liquid hydrogen systems development. And he was actually my mentor as a co-op at NASA, so fun fact there too. So Matt, do you want to say hello?
Hi, Monica. Sorry, I would have made a shorter bio. I didn't realize you were going to read the whole thing.
No worries. And then lastly, but not leastly, we have Jacob Roth. So Jacob started in the fluid behavior side of CFM with a particular focus on low gravity slosh and droplet modeling. And he's also recently done some work with large scale tank pressurization systems, including both inert and autogenous designs. So Jacob, do you want to say hello?
Hi, Monica.
Hi. Okay, so I'm going to go ahead and leave this up unless folks are turning their camera on. I want to turn my camera on though, and I don't know how to do that, so I'm going to stop sharing for a second.
I have not figured it out either.
That's all right. That's okay. We can just talk. So I will put my screen back up just so folks have something to look at. I'm going to have the chat, looking at the chat, so you guys are welcome to ask questions as we go through this. I definitely encourage participation from the audience. also, I have some questions for you guys too that I'm going to be asking you. But I just want to say before we start, we have a very diverse panel. So I think we have nearly every aspect of modeling covered, from research to launch vehicles to first order to CFD. So appreciate you guys and the diversity of thought here. So I'm going to start off with our first question. I just want to ask you guys. We'll start at the beginning. So we'll talk about inputs. So when you're building your cryogenic models and for your different applications, what kind of inputs are important to you in preparing your models? And then where do you usually go to get them? Whether it's a person or another model, data books. So whoever wants to just kind of take it on the panel, go ahead, or I can call somebody. All right, Cindy, I'm going to start with you because you're the first name on the list here.
Okay. Let's see. NIST is one. We use RefProp some for some of our properties. There's several older NASA books and some others. I'll have to get the names and I'll put those in the chat.
Right.
Different properties. So.
Anybody else have different sources for properties or having to integrate? Well, let's kind of talk too about integrating. So any of you actually have to integrate your models with other disciplines or other CFD codes? There's Matt. He figured it out.
I figured it out.
I'm still working on it. Oh, now I found the button. Okay, I'm here too. I was hoping to have a background on though. So I got distracted by my camera. So do you have to integrate your model, say with another discipline, maybe a structural or another thermal analyst that's doing more systems level, or with other CFD disciplines or other crowd disciplines like a CFD analyst versus a first order, integrating with first order. So and how do you find what's the best way you find to kind of exchange that information as you're integrating? Matt, do you want to?
Well, I can say, this is Jacob.
Jacob,
I can say for ours, we've done gone the whole gamut, I would say, with combining the different codes. We've gone the route at times of file passing or passing kind of fairly simple things between the different codes, all the way to some of them now. So a lot of the new systems have built in, or have APIs that we can call across and co-solve. So that becomes an easier thing in some situations. So, it really depends on the rate of the two solvers or three solvers or more, and whether they're sort of compatible, and whether you should, complete a solve and then just use that data versus whether they should work together. So it's really tough to make it a generic thing. But I am been impressed as things have gone with, Python with some of the new codes and stuff. There's a lot of things we can do now to help make those things run smoother together.
When you're looking at that, do you find it's different for every single analysis you run, or every single kind of application you have to find a different way to make them work together? Or do what do you look for as the main thing to help you make a decision on how you're going to integrate?
Yeah, I think it's hard to make it too generic. I mean, if you're using the same codes over and over again, then the methodologies you can use to pass data between those can be somewhat more consistent. But when you're spending time with changing up which codes you're using, then yeah, it tends to be a little more one-off.
Okay, thanks. Matt, in your first order models, are you pretty much doing the full system, or are you drawing inputs from other analysis models or other analysts?
It's a little of both, Monica. I tend to model, interdisciplinary things because it is a system model. So that's usually the easiest way to do it. But then there's a lot of back and forth with the other team members that are doing higher fidelity models to make sure I'm bringing in the most up-to-date information and averaging it in an appropriate way, for example, our bulk fluid properties or that sort of thing. So it tends to vary, I think, similar to Jacob's answer. I'm not sure that there's a standard approach. It kind of depends on what they're using but you know, it's a few minutes of conversation, and we can usually find some way of you know, passing that information back and forth.
Okay. And Dan, I know you and Olga often interface with CFD, or is there a I think sometimes you may be modeling something in Thermal Desktop that is getting some inputs from CFD or vice versa. Can you talk a little bit about that, and if you have any tips or experiences on what works and what doesn't when you're trying to do that kind of integrated look at a system?
Yeah, so for instance, with like tank self-pressurization for storing cryogenic propellant, we typically, typically have a thermal desktop nodal model that will predict the heat loads going into the tank, and typically what we've done in the past with cryogenic propellants, if the temperature of the liquid doesn't vary significantly, the heat loads stay relatively the same during the transient. So usually what we do is we run the thermal desktop model and predict what the heat loads are going into the tank, and then we'll take those heat loads and put them in and use those as inputs into the CFD model. And they're steady state heat loads. They're steady state heat loads in a transient CFD model. And that's usually been that's worked pretty well, especially when we've compared the model predictions against some of the experimental test data. But there are cases where that heat load can vary, particularly if the temperature of the tank is changing during the storage duration.
Okay, so what would you do in that kind of application?
You'd run a thermal desktop model and predict the heat loads going into the tank, and then you'd get zones where those heat loads are coming in, then you'd apply those heat loads onto the tank wall, onto the outside of the tank wall, and then the CFD model would solve for the conjugate heat transfer inside of the tank and within the tank walls themselves.
Okay. Thanks, Dan.
Also, I wanted to add that sometimes experimental description is lacking some information, like in a recent case that we've modeled. And thermal desktop has been helpful to identify, for example, a pressurization, gas pressure and flow rate that we can use in CFD to get to the initial conditions of the next test. Things like that.
Thanks, Olga. Thank you. And Alok, do you have a different kind of experience with primarily working GFSSP? We gotta unmute you. All right. Can we unmute Alok? There he is. Okay.
Can you hear me?
Yes, sir.
Okay, so sorry. Yeah, we have been trying now to have a kind of a coupled analysis with CFD group right now here. This work is in progress right now because one of the thing is quite challenging for the CFM modeling, particularly with the nodal code, is to get the right correlations for the heat transfer coefficient and the friction. And one of the problem in the CFM area is you are kind of working with the two-phase flows, and for the two-phase flows, both friction and heat transfer correlations, what you need are not really good for the cryogenic fluids. There have been a lot of work with the water and the refrigerants, and over the years they have developed very accurate correlations for the heat transfer and the pressure drop for room temperature fluids. But when you come to the cryogenics, there is a big difference. You might say that, oh, it's a phase change. Why cannot you use those correlations? But the problem is in the properties. The cryogenic properties are so different than the water and the refrigerants. And the correlations which have been developed for that is not really applicable, not very accurate. Particularly if you look into the density ratios between the liquid and the vapor. For water, its ratio is almost 1500, whereas for hydrogen it's only 50. Same goes for the surface tension. I mean, water has a surface tension probably 100 times more than hydrogen, and that really determines the bubble size, which has got a very strong dependence on the heat transfer coefficients and the pressure drop. So that's the reason we need probably very good correlations which are not available. Good news is that there are a lot of work currently is going on at the University of Florida and the University of Purdue to come up with the cryogenic correlations, which will really help us a lot. And we are currently trying to develop both thermal desktop and the GFSP model where the entire boiling curve can be implemented. So it will really help the analyst quite a bit. The other question is really that where CFD can help. Two-phase flow boiling heat transfer coefficient calculations by the CFD is probably will be a little bit more difficult or challenging. So what we have been trying to do right now is to develop some collaborations with the CFD group to give us the heat transfer coefficient for single phase. There are a lot of areas where even we do not have a good correlations for the single phase flows, like pressurization under stratified conditions. And in those areas, probably CFD can help us a lot. So what we have been trying to do right now to develop some heat transfer coefficients from the shear stress, because the CFD can give us the shear stress quite accurately in very complex flow situations. And there are some analogy, like a Reynolds analogy, Chilton-Colburn analogy. They can give you the heat transfer coefficient from the shear stress. So we need to do some more validations work, but that's one of the work which are currently going on, and we kind of look forward to see that gives us, because this is really a problem for the nodal code to get a good correlations for heat transfer coefficient. I don't know whether I probably talked too much, Monica. I've kind of deviated from what you said, but I just wanted to mention that, yeah, I mean, we are trying to get a collaborations with the CFD group, if CFD can help us to get a good heat transfer coefficient.
That kind of opens up another question I wanted to ask, which is model validation. Sometimes it's difficult in cryogenics. I know there's been a lot of efforts in the cryo modeling portfolio project to get more access to more flight data for validation, but that's not always the case. And I think every application is different. So could you guys talk a little bit about how you validate your models? And what's most valuable for you from the data you're using for model validation? What types of things you look for?
So Monica, I work for the Launch Services Program, and so ours is, we have, I should say, be happy with a large amount of flight data, and that, the biggest problem that we see a lot of times is that we get the flight data that the data is not exactly where you want the data to be, right? You're getting flight data, but it's for a temperature that's 3 steps away from the actual thing you wanted the temperature of, or, there's always these separations. And so oftentimes we're building bigger models to encompass more things to try and get to where that temperature is in order to kind of correlate. But obviously then you end up with a lot more unknowns on the little details inside the tanks. You know, when you're trying to get the temperatures and you're talking about, well, now it's way up here on the sidewall. So there's a whole lot of things that could have gone different before you get down to the actual temperature of the, you know, the cryogenics. And so, you know, for us, we're sort of more concerned with like the end result of the flight data. And so that can work and that can be nice. And that's kind of how we will tend to validate our models. To be desired on the sciencey side of researchy side of things, because you still kind of don't quite know exactly what happened inside the tiny details.
Yeah, thank you, Jacob. That's great. And Cindy, do you kind of have that? I know since you're both at LSP, do you have a same experience or anything to add?
Yeah, in most of my stuff I've done, I've been fortunate to have data to, you know, correlate the model with. Even when I was doing the superfluid helium, they were already and had already done their testing, so I already had data to match what I was modeling.
Okay, thanks. And then, like, I'll go to Olga because we haven't heard from her in a minute. So, Olga, how about you with CFD and supporting some of these other modeling efforts? I know you guys are doing some validation efforts, but also looking at new concepts. So, how do you kind of look at validation, and what kind of data do you get when you're looking to validate your models?
Yeah, it is important to validate the models before they're applied to this other design, for example, of experiments, or when we're trying to answer some questions for SpaceX. So the model validation, we mostly compare with pressure, temperatures in the tank. That's what's mostly available from experiments. But sometimes, just like Jacob said, that it's important to have data in the strategic places, let's say. For example, we modeled a ZBAT experiment, and there was a pressure transducer that was producing some heat. And we didn't have any temperature measurements in the vicinity of that pressure transducer. So we had to kind of guess and envelope our predictions around with different heat inputs in order to say if it's important, how much it affected pressure temperatures in the tank. Some things that are rarely available from experiments but are highly desirable is more diagnostics, like, for example, visualization is very helpful. In most of the experiments, we just have pressure and temperature, so that's what we have to use. What also could be helpful is to have more temperature data near the interface, so we can see that temperature gradient on liquid vapor side. But for example, again, the example of ZBOT, we had some DPIV data from ZBOT, and it really helped us with our model validation, because we were able to confirm and put it as an input in our CFD model that during jet mixing, for example, that jet was coming in to the tank at an angle when we designed and expected it to be straight along the tank axis. So that helped us to explain some phenomena that happened during experiment. Yeah.
So would you recommend then, as we look at designing, you know, specifically as we're looking at designing some experiments intended to get data to validate our models, thinking in advance, for example, with your pressure transducer, do you think if we had temperature data at that nearby, it may have helped us model that better?
I think it's helpful to have some input from the modelers during the design of experiment. Of course, ZBOT had that input because, you know, I'm on the science team, so we've modeled, ran a lot of models prior to experiment, but we just didn't think about the pressure transducer, that it might be a problem. So now we're working on ZBOT NC, and we want to put temperature measurement there near that pressure transducer. So kind of learning from experience. But it's helpful to have some input from modelers on what's helpful in the specific experiment for future model validation.
Thanks, Olga.
Thank you.
I think hopefully somebody learned something too today. If you have a pressure transducer, watch out for the heat.
Yeah.
Dan, you have anything to add?
No, I just I think I think it's important, you know, to note that I think when you run a test to follow through with the test plan and keep all that documented, because when we in the past we've modeled tests like some of the CPST ground testing or the EDU testing. We've attempted to model a pressurization test. We found out that the model wasn't matching the experimental data very well, and then when we reviewed the test reports that the test conductors wrote after the test, we found out that one of the reasons why it wasn't matching the experimental data was because the test didn't go as planned. They ended up venting the tank in the middle of it, and that affected the initial conditions, which affected you know, how well we were able to model the test. So I think you know a high quality test and also documentation is important.
Okay, yeah, that's a interesting lesson to watch out for too, as we try to dig up some historical data, checking to see if the data, making sure you understand exactly how it was run. How about you, Matt? I know because you're working more on first order modeling, so validation probably looks a little different than it might for CFD or thermal desktop.
Yeah, it's actually come back to bite me on some of the tests I did early on now as we're trying to validate them, and I'm working with Olga and Dan and others. It's interesting, and I don't know what the way around this is, but it kind of fits in with what Olga was saying and Dan as well, that at the time you run a test, you tend to instrument it and document the things that fit the modeling technology of that time period. So there's a lot of bulk information and generalized positioning of things. And now as we're going back and trying to validate that with CFD, which was not very advanced at the time a lot of these tests were run, the exact position of certain things is important, and we don't have that data, or dimensions that weren't really critical at the time the test was run. That's a little bit of how do you look into a crystal ball and know what kind of modeling you're going to need in the future. But to the extent you can, it's helpful. I think definitely the other comment about knowing how the tests are actually run. It's amazing what you learn from the authors of these tests or the test conductors, like Dan was saying, that happened that isn't necessarily well documented. And or they'll say, well, don't look at that test because this or that happened and we weren't sure. This sensor went out and we didn't really say that in the report, and that's a difficulty. The other thing that's kind of, and I don't know the answer to this either, but I don't know what the good method is for storing and making raw data available looking forward into the future, because we've also run into a lot of tests where it's like, wait, for the folks who ran the test, we remember taking that data, but who knows where it's at? It was recorded either locally or it was recorded on a system that's no longer in place. And it's kind of interesting. We publish things, publishing hasn't changed a lot in terms of journal reports and other reports, other than you can get them online now in PDF format, but we don't really make available very often the actual data and even though we have the ability to, we can store a lot of data if we chose to. So again, I'm not sure what the solution to that is, but it seems like that would be more helpful with some of these validation exercises.
Yeah, that sounds like a good topic for the TFAWS greater community as we move forward, is kind of looking at even beyond cryogenics. Is there a way that we can do a little better as we move into digital transformation? Can we make data better available after test complete? And look, I won't leave you out. So if you have anything you'd like to add.
Yeah, I think it is. Um, it has been really a challenge to understand the data, and lately, I'm trying to validate some of the tank filling model with some of the cryo experiments that was done earlier at Marshall, and it takes a lot of time for the analyst, to understand the hardware. So I thought that, it's always my advice would be from my experience that, one really needs to understand quite a bit of the time to understand the data properly, and of course, all the answers that will never be answered. All the questions will never be answered. So sometimes some critical judgment is necessary to use the data, and that really comes from the experience and comes from the. I have seen that the more you talk with the experimentalist, it's always a better, because you understand the test data much more. So, and I mean, I don't have the answer, but what I'm experiencing, more communications we make with the experimentalists and the analyst, the things is going to work a little better.
I'm hearing a common plea, I think, in as we document the testing we do, being as thorough as we can, and even in the design, trying to anticipate what others may want a few years from now. So the more you can document it, it sounds like the better. Even in ways, even things we don't think we need, like line diameters and lengths and precise location of sensors. So that's and the impact those sensors may then have on your system. As we add instrumentation, we may be inadvertently adding heat load, like Olga mentioned. So that's all really good, I think, takeaways that are important as we do cryogenic systems. So thank you. So I think you mostly have covered it, but if anybody wants to add, is there one thing, if you could tell somebody that's designing a test to add to their system to make your life easier, what would that be? Anybody can chime in.
Can I tell something, Monica, here? One of the things, as an analyst, we have seen that flow rate data is not available for many experiments. If you do a cryogenic experiments, particularly the two-phase flow experiments, getting a good flow rate data is very, very important for the validations. Most of the time we get the pressure data, temperature data, but in many cases we don't have a very reliable flow rate data. So I would suggest, if you, for the future designer of the experiments, to put more emphasis to get the flow rate data, particularly for the cryogenics.
Okay, thanks. Anybody else have a wish list? Oh, and I see Cindy added the sources that she was mentioning earlier on properties. So if anybody's interested, she added that to the chat. So thank you.
Yeah, I added that to the chat. Well, if you're doing an outside experiment or even sometimes inside, knowing what your environment is in the outside or in your test facility can sometimes help.
Yeah, that's something I think we overlook a lot. We don't think about the ambient conditions we're sitting in. We're not always running thermal vacuum. So that's
Right.
a good point. All right. Well, while we're talking about things we wish we could have, I want each of you, if you could just, what is the biggest gap you see right now in our ability to model cryogenics? in cryogenic systems. It could be anything to do with how you do analysis, to the data you're missing, to maybe an entire application or a tool that you think would be helpful. But what do you think the biggest gap we have is in our modeling capabilities right now? I'll give you guys a second to think, and then the first one to the mic wins. All right. Jacob, I'm going to call on you. I'm going to pick on you because you're right under my head right now.
All right, there you go. Yeah, my positioning got me again, huh?
Yep.
It's a tough one. I think that we are sort of in many ways spoiled for a lot of the tools that we have now. There's so many, and they continue to grow. Obviously, getting all of the data that we constantly work to try and get areas that we might not know very well is important. But honestly, I think that at least for my side of things, we do a lot of, like I said, the low gravity type stuff, and those are tough because you're in a regime where your inertial forces aren't dominant anymore, and that sort of, as we like to say, chaos reigns. And so sometimes the really tiny inputs mean really different end results, and sort of that standard chaos theory. And so some of the things we've dabbled with that I would love to see expanded in the future is some of the probabilistic type behaviors for some of those things. Sometimes you don't know the exact initial condition, but you kind of know close. How different can your end result be? How different can those things end up? Because I'm going to have a really hard time getting the exact initial condition, but I might be able to do a better job of bounding it. So, for those types of solvers are really tough. It's really tough in like CFD to do those kind of things. You give it an initial condition, it gives you an answer, but it doesn't really tell you what it could have been. And that can be really important for a launch vehicle or something. They really want to know, like, okay, but was that is going to be as bad? And so how we quantify those uncertainties, how we handle those types of propagations, I think is something that we definitely need to handle as an industry.
Okay, thanks, Jacob. Who are you, Matt? Since you're to my right.
I think Look did a nice earlier conversation about some of the data that or correlations that aren't really well suited to cryogenic fluids. And then, I think that ties into what I just heard Jacob say too, in the low gravity situations. I don't know if it's a gap necessarily, but maybe a sense of confidence that maybe isn't always justified with some of our modeling where we're using built-in correlations or built-in techniques of generalized codes, particularly probably commercial codes. This is something I'd be careful with, I would assume, that don't really apply to the situations we're in. And I think I would, it's interesting. I hadn't thought about it till the way Jacob described it, but I would piggyback on that comment, the idea of sensitivity analysis or parametrics or uncertainty around. There's some codes I think that are starting to build that in, but in terms of the codes that we tend to use, the higher fidelity codes, it would be interesting, and this is maybe a wish list, but to be able to push a button and say, what if this or that variable changed by 10%, or was, how does that, as Jacob said, propagate through the rest of the results in the analysis? I'm not sure I would call it a gap. Maybe it's a feature that would be nicer or easier if it could be more easily implemented, I guess, in current models would be nice.
We'll take notes. How about you, look? Because I know you mentioned earlier you're looking for those correlations.
Yeah, I'd like to add that, is the microgravity environment. Our data on the microgravity environment is really missing. That's one of the area. Of course, I was mostly earlier talking about the two-phase correlations, but I just wanted to say that we have very little data on the microgravity environment. Of course, it's very difficult to do those experiments. You can do something by parabolic flight, which is less expensive, but you can get some data. But doing experiments in the orbit probably will be another area we can get some of the data, both friction and then the heat transfer. So I'd like to add that to my wish list. For the but I completely agree with also with Jacob that the uncertainty is one thing. How you really do a good uncertainty analysis for the numerical modeling. There have been a lot of work has been done for the experimental uncertainty, but numerical uncertainty is another area we all need to work out so that we can give the designer a kind of a band and they can work on that one. So I hope in future most of our codes will have that kind of capabilities to give an uncertainty band, but it's not easy to do that one. So but the best thing probably would be for the analyst to just to determine what is the most sensitive parameters. And I mean, one of the things we always do is the heat transfer coefficient, because we know that it's a lot of uncertainty. So whenever we do some analysis and do some uncertainty on the heat transfer analysis, and we tell our customers that, yeah, our results are good, within this band.
Okay. Thanks, Alok. How about you, Dan?
Yeah, I think Jacob kind of hit it on the head, and we're kind of spoiled in 1G the liquid settled, and you can kind of predict the behavior and initial conditions rather well. But in low G, where the capillary forces dominate the body forces, the physics become not intuitive and hard to predict. And it's also the low G environment also results in a lot of chaos that occurs in the tank, during events, similar to sloshing and other things. So it adds a lot more challenges to those models, in particular with CFD. The interface location, is known in 1G. So you know where the liquid vapor interface is at. In micro G, that gets a lot more complicated. And now the current CFD volume of fluid models that we use, it gets a little bit more harder to predict the heat mass transfer at the liquid vapor interface, to predict the ullage collapse or the pressure at usage, for both the storage and also transfer. Transfer, it affects the predicting the pressure and temperature in the tank, and both the receiver tank and also the donor tank. The donor tank, is important to be able to model correctly, because you need the pressure in that tank, especially if you're going with a pressure fed transfer. You want to make sure that delta P is available.
Yeah, that's a good note.
And then another thing, with CFD, we have good laminar models, and we can model the Navier-Stokes equations with laminar only models. The turbulence models that we have to use are based off a single phase flow, and they haven't really been developed for two-phase flow, such as condensation at the interface, which that can affect the pressure and condensation, such as pressurization of a tank, autogenous pressurization. A helium pressurization is a little bit nicer because it doesn't condense, it doesn't collapse. Where with autogenous press, it's a condensing medium.
Yeah, it would be nice to get some flight data on some autogenous pressurization. All right. What about you, Olga? Do you have any different things, gaps or wish lists of kind of what's missing?
I was going to talk about turbulence modeling, which Dan just talked about, that just like others were saying that existing models or existing correlations are not quite applicable to cryogenic tanks. So let's say in turbulence modeling, Raining's average Navier-Stokes models are very well applicable and tested and useful for other types of flow, external aerodynamics, for example. But unfortunately for cryogenic tanks, they're not performing that well. And we are forced to use laminar models for a lot of cases. Some models more advanced, like large eddy simulation, we're able to apply, but only in limited conditions. Like, for example, we use them for modeling jet mixing in Zibat tank, but only for a short period of time, like maybe a minute or so. But when we need to model, let's say, 6 days of pressurization on the lunar surface, something like that, of course, it's out of the question. So there is a need to develop better turbulence models that will better represent the interface for cryogenic systems. And with that, we probably need to do some experimentations with using more advanced, like large eddy simulation models. And for that, we of course need a lot of computer power, a lot of computer nodes, which we've been very lucky with the Cryo project before and CFM modeling portfolio now. They added a lot to our existing cryo cluster that we're using. So we're very grateful for that. It helped a lot, but we need to definitely expand our computer power. So, yeah, that's all I have to add.
Thanks, Olga. Definitely could use, we can all use more, but definitely in the area of CFM or CFD, we could always use more computer power.
Yeah.
And then Cindy, did you have anything to add?
I think everybody's pretty well covered it.
Yeah, I appreciate that. And you know, as we move forward in the with NASA's projects and then also with the technical discipline team, these are all things we can talk about and take away from this and talk about as a community. So appreciate the dialogue. I just wanted to read, there's a chat comment from Doug Westrom, and he just said, for the testers, sight glasses for two-phase flow are very helpful, and also added that adequate pipe lengths for flow meters are very important, which is something that I personally have seen not necessarily remembered when planning out a test design. So those are two good notes to take with us. So I think we have time, just real quick, one last question before we wrap up here is, if there's one thing that you could tell somebody starting out in cryogenic modeling in your area, just one note you could tell them, a lessons learned or a heads up, what would it be? So Cindy, we ended with you, so we'll start with you.
Yeah, okay. Start small. You know, don't add a lot of complications into your model to start with. You know, get it working, particularly with thermal desktop and all that. Just get it working and then slowly add your complexity and check with hand calcs.
Yeah, always a good note. I'm going to go in reverse order for our last one. So I'm going to ask you next, Dan. I guess Olga would be next, but I'm switching it up. So Dan, what's your one?
Yeah. I think the one that Cindy commented on, start small, is a good one. I always say just don't try to build a super complicated model, because there's likely a good chance if you're doing it for the first time, it's not going to run. But yeah, if you start build up and take baby steps, adding capability to the model, you'll get it to run, and you'll gain confidence in, I guess, how to use the tool. The other thing I would recommend, I think Cindy hit it on it a little bit, is use hand calculations just to verify your model. But I think in order to use your hand calculations, you really have to understand the two-phase physics of what's going on. So, you know, really try to dig into those hand calcs, even if they're back of the envelopes, just to do sanity checks to make sure your model is predicting the right thing.
Good advice. And I actually, my very first model I built was a thermal desktop model that I decided to start with like 50 some nodes and it wouldn't work and I couldn't figure it out. And then when I built a 3-node model, all of a sudden I realized what I just had started way too complex, and then I could kind of build from those 3. So start small is advice I could have used when I was starting out. Olga, how about you? Do you have words of wisdom or advice for anybody?
It's actually quite similar to what other people just said. Start with simpler models, learn more about the code, run some experimental cases, some grid studies, just to get the feel for how numerics reacts to these things. And don't be discouraged if things don't work. That's normal. That's how it normally is. And then you keep working on it, and you solve the problems, and they start working. So
Yeah, I like that. Don't be discouraged, because we all want to. We're all NASA engineers. We all want to succeed, or aerospace engineers. You know, we're usually pretty motivated people. We don't like when things go wrong. So that's good advice.
yeah, but things normally don't work initially, and that's something that happens with every project I've modeled. So just keep moving, and it all will be resolved.
It'll converge, right?
Right. Eventually.
Alok, how about you?
I think Cindy had hit the nail by telling 2 things. Start small and do the hand calculations. I think I cannot agree more than 100% on that one. And Dan also mentioned that, about the properties, for the two-phase flow, understanding the two-phase properties is something, is very important. And we have done that. If you look into the GFS manual, we have got 25 about example problems, and none of those, I mean, probably 90% of the models are only 4 or 5 node model, because you just take one thing and just try to explain that physics with the 2-3 node models, and then you go to another problem and just you understand the physics on that one. So starting small is the best advice, for those who are starting their CFM career.
Thanks a lot.
Thank you.
And then Matt, do you have anything for us?
I echo the great suggestions already made. I may be building a little bit on Cindy's comment. I think you can also, in addition to running hand calcs, maybe try to bound the problem. Sometimes you can find a way to say, all right, it's not going to be any less than this, and it's not going to be any more than that, just to oversimplify things. And sometimes that gives you some confidence too. And the other technique I like to use is trying to come at a problem independent ways and see how close the answers come out. As another way to kind of give you some confidence in your results. The other thing I would leave with folks that are just, I think part of your question was people who are beginning in this field. A couple of textbooks over the years that I think seem to continue to hold their value in terms of helping people understand sort of some of the not terribly intuitive things about cryogenics is Thomas Flynn's Cryogenic Engineering, which I see is still in print, and they actually have a paperback version of it. The last time I looked, it isn't too bad, like $50. Yeah, it's like over 1,000 pages. It's a real tome. And the other author, Randall Barron, who wrote one of the early classics, but I like actually even better his cryogenic heat transfer. He has a recent update of that. I would highly recommend that too, because it really takes you through the fundamentals of heat transfer and then contrasts that with the things you've got to think about when you're in a cryogenic region. So those are 2 authors that I found seem to always be the go-to ones I keep pulling down off the bookshelf. So for folks starting in, I would recommend those.
Okay, great. Thank you. And we'll maybe we'll get those posted on the website too.
And I can put it in the chat too for people who are looking. I'll do that.
That'd be great, Matt. Thanks. And then Jacob, we'll leave off with you.
So, I mean, I think they've given a lot of great advice to the people who are just starting out. The other thing I would give too, maybe that we didn't touch on, is that a lot of times when people are first starting, they get models from other people, working models that they've got to mess around with. And kind of like what Olga was saying about being disappointed, I would encourage you not to be afraid to use save as and break the model. Sometimes finding where it breaks gives you a lot of information to understanding how it works. You know, and so if you're not starting with your own model, but you're starting with somebody else's model, don't be scared of it not converging all of a sudden, because that just helps you understand what's right, why it works, and what you might be able to do to make it better.
I think that's really good. That's good advice. Thanks, Jacob. And I just want to say thanks to all of you. I'm going to talk to our sponsoring tech fellow, Mike Meyer. I am his deputy. So I just kind of want to put a plug in for NASC. We may try to get this posted on NASC Academy. I'll talk to him about that, but we'll definitely have this posted on TFAWS website also. So appreciate you guys participating in this, and I think got some really great takeaways and thoughts for discussion. Hopefully we can continue having panels like this in future TFAWS and maybe build on them in person.